Okay, we need to analyze what the step response of second order system. That we have to analyze. I don't know. बुरहान हमीद ये कौन है?
यस सर, ये
तंजीब.
भी है क्लास का ही।
Okay. Now our first objective here will be the first aim is to define the transient specifications that will be associated with underdamped response. So first aim is to define the transient specifications related to underdamped response. So we have to look into the transient specifications first. Now second, next aim is to then we have to relate these specifications to the pole location. Next is to relate these, what are the specifications we'll be getting, these specifications with the pole response. Sorry, with the pole, not response, location. With the pole location. And then what we have to draw? We have to draw association between the pole location and the underdamped response. Then we need to draw the association between pole location and underdamped response. Okay, that's what we have to do. Now let's begin. Some people are joining this, I don't know. Who is this? Saqib 5058 and Tanzib
यस सर, साकिब है।
501
यस
64
सर, दोनों।
Musab.
यस सर।
Okay, let us begin now. We have to begin this by finding the step response of the general second order system. Finding the step response of step response for the general order second order system. Okay, I don't know why there 56 is, who is this 56?
यस सर, शाहिद नजीर।
67
यस सर, ओएस।
43
यस सर, साद एंड शारिक।
Okay, so let us begin. So we have second order system general as omega n square divided by s square 2 xi omega ns plus omega n square. That's we know this. The transient response C of s is the Laplace transform of input times the, so C of s we can obtain, C of s will be input, that is R of S into G of S, that we already know. For what we will be having here, xi less than 1, because this is an underdamped system. Here what will happen, closed loop poles are complex conjugate. Shahid, is another there, 15, 17.
Yes, sir.
So closed loop poles are complex and conjugate. Okay. Okay. And they will lie on left half of S plane, that you already know. Everybody knows this. Therefore, we can write down closed loop transfer function is, that means C of S divided by R of S is equal to what? C of S by R of S will be equal to omega n square divided by S square plus 2 xi omega ns plus omega n square. Okay. Now we can write, because we have step input here, so RFS will be 1 by S. We are using step input. So therefore C of S will in this case will be 1 by S into S square plus 2 xi omega ns plus omega n square. So this is what we are getting. A simple manipulation I will be doing here. What I will be doing, I will write this as 1 by S minus what? S plus 2 xi omega n, sorry, divided by the same thing, S square plus 2 xi omega ns plus omega n square. See here, if we cross multiply this term will come S square plus 2 xi omega ns plus omega n square. I will subtract this term from the S plus this 2 xi omega m from this term. So left over will be S square. Sorry. Yes. Here, if I multiply this S square plus 2 xi omega ns, okay? Here this cross multiplication, here S square plus 2 xi omega ns plus omega n square minus S square plus 2 xi omega ns. So this will get subtracted and we'll be left with 1 and the same denominator. So we can manipulate this, and you can use the partial fraction also, but this is simple manipulation we can do here only. So I'll write this C of S equal to now, okay, I'll write this 1 by S. I don't have any problem for this getting Laplace inverse, but I have to see what I can do for this in order to get the Laplace inverse. So I will write this xi omega. I will break down this to 2 plus xi omega n. 2 xi omega n. I'll break down this to 2 terms. Okay. So denominator I will be having S plus xi omega n S whole square. How I can get this? Let me write it for you. Okay. So I can write here, same, take the coefficient of S, make it plus positive 1, take the coefficient of X, that is, here we have S, that is 2 xi omega n, half it, and then square it. This and this will get cancelled, omega. So this is equal to xi square omega n square. So I have to add it and subtract it in order to make it a perfect square, that you already know. So that's why I will keep it separate. So that should be xi s square plus k xi omega ns plus omega n square. I am not writing anything. Now I will add this and subtract this. Xi square omega n square minus xi square omega n square. So this I have added and subtracted. Okay. Next step for me will be, I will try to make it a perfect square now. 1 by s minus, okay. So this term I will keep it as it is. Xi omega n plus this I will also going to keep like this, okay, divided by, so this s square plus this first second term and plus xi square omega square will make a perfect square. That will be s plus xi omega n whole square. So first, second, fourth term leftover will be plus omega n square. I can take common omega n square, and then 1 minus xi square I can take common. Okay. So let us say I'll be writing this omega d as omega n into under root of 1 minus xi square. Let us say this term, for simplification's sake, I will write it like this. So simplifying this further, C of s will be equal to 1 by s minus, okay. So what I will be doing here, I'll write this, what I will write like this here, please see, I will write this as it is, no problem. Now I will divide this term, I will divide this term by 1 by under root of xi square, and I will also multiply this by 1 minus under root xi square. Okay, this is in the numerator what I will be doing. And the denominator, see denominator what I will be doing, denominator what I will be doing, denominator this is as it is, s plus xi omega n whole square. This is a square of this. If you make a square of this will become omega d square. This I will write as omega d square. I want to get Laplace inverse. That's why I'm doing all these manipulations. Okay, here we are. This step, I think this up to this step, there is no problem. I'll bit simplify it a bit more. Okay, so I'll write it like this. 1 by s minus s plus xi omega n, okay, and I will break down this to s plus xi omega n whole square plus omega d square. One term I will make it like this. Second term I am going to make xi, this I can write omega d divided by under root of 1 minus xi square. Okay, then we have the same term s plus xi omega n whole square plus omega d square. So this I am writing like this. A bit manipulations I have done. I have separated the two terms and denominator I have kept the same. Okay, this is what we have for the time being. Okay, now if you remember last time I have told you Laplace of a e raised power minus at cos of wt was equal to a s plus a divided by s plus a square plus omega square. And on the similar grounds, we had Laplace of a, sorry, b, not a, Laplace of b e raised power minus at sine of omega t, I can write this as b omega divided by the same thing. So I'll try to get it in this form. This is my objective. That's what I have last time showed you also one example. Okay. Now you can see here first term. Okay, s plus a is in cos term. So a here is what? A here is 1 very clearly. And if you can see second term, b omega. Okay, so b is also 1. B term is also missing, that is b is equal to coefficient is 1. Now a, s plus a, instead of a there is what? Instead of a there is xi omega n. Okay, instead of a there is xi omega n. Okay, now let me write this as taking the Laplace inverse above equation. So what I will be writing, C of t will come out to be 1 by sc. Step is 1. Laplace inverse, sorry. Laplace inverse is 1. Okay, minus. So this term, this term will be like this term. A is 1. So that will be e raised power minus 80. Minus 80 is minus xi omega and t. So a is 1, we don't need to write it. E raised power minus xi omega and t according to formula cos omega t. Now cos omega t, omega instead of omega there is omega d. So cos omega d t. Fine. Second term, z divided by under root of 1 minus, sorry, xi divided by under root of 1 minus xi square. Omega d will be as usual. Okay, just a second. Yes. Is it correct or not? Above we have taken xi omega. That should be omega d. Yeah, fine. So xi omega d will be there, and this is a constant term. So this term, no, sorry, just a second. Okay, xi, this is fine. Now omega d, instead of omega, there's omega d. That's fine. That we know already. So this is omega d. That's why the b is 1. So omega d s plus omega xi n whole square plus omega dc whole square. So this will be like this. B is 1. So it will be e raised power minus at, that is xi omega n t. Okay. Then it will be sine, as usual in the formula, sine instead of omega, it's omega d by t. So this is the complete formula. I hope this is not so difficult to obtain. So C of t can be further written as, that will be equal to 1 minus. So what we will be doing here, we'll try to get this e raised power minus xi omega n t and under root common. See, 1 minus e raised power minus xi omega n t divided by 1 minus under root of xi square. So inside the brackets, this has gone. So we need to multiply this in order to balance it by 1 minus xi square cos omega dt plus. So here only leftover will be xi, e will be gone. This will be divided by will be in the common. So xi sine omega dt. Up to here, I think there's no problem. Now after that, we can further write C of t can be further written as, okay, this is fine for us. So before writing the C of t here, so let me write one formula. If you remember 11th class, sine a plus b was equal to sine a cos b plus cos a sine b. I will try to utilize this trigonometric formula. How? Let us see. C of t, I can write. Okay, now what I'm trying to do, I will try to use this trigonometric formula. Okay, now here what I will try to do in order to get sine A cos B. So for me, what should be sine A cos B? Sorry, this is formula is what? Sine A, let me get the exact formula. I think it should be sine A sine B. Sine A, is it correct? Sine A B, sine A plus B is correct. Sine A cos B plus cos A sine B.
Yes, sir.
I
Yes,
think
sir.
this is correct formula. Yeah, yeah, this is correct. I think this is let me remember. Second quadrant sine plus B third quadrant. Yeah, it should be sine A. Sine, then that is another. Yeah, that is fine. So let me put it in this formula: sine A sine B. So wherever cos have, I have to make it let under root of 1 minus xi square should be equal to sine of phi. This is let. I have to assume it. So I will make xi equal to sine A cos B cos phi. Now what, substituting these values, C of t will become 1 minus e raised power minus xi omega n t divided by under root of 1 minus xi square. This is very important formula. So derivation we are doing based on this, there are lots of numericals. So this will be sine phi cos omega dt plus cos phi sine omega dt. Okay, so this is nothing but sine A plus B. So C of t we can further write as 1 minus e raised power minus xi omega n t divided by 1 minus under root. This, this I can write sine of A. A is phi plus. So I will write down this as sine omega dt plus phi. Okay. So this we can write it like this. Okay. Sorry. Let me erase this. Okay. Okay, have a look at this. Now at t equal to infinity, that is, we have a steady state time. What's going to happen? C of infinity will be equal to 1 minus e raised power minus infinity is 0, so that will be equal to 1. So we will have a steady state value. Okay, e raised power infinity. So we will have a steady state value. E raised power minus infinity is 0. Now two times are very important for me. At t equal to 0, what's going to happen? At t equal to 0, so C of 0 will be equal to 1 minus anything raised power 0 is 1. That will be 1 by 1 minus 1 by under root of 1 minus xi square. Okay, into sine of phi. T is 0. So that I can write here is sine of phi. Okay, because this t is 0. Now we will draw a damping ratio triangle, we call it. Let me draw that. Damping ratio triangle. This is the triangle we have. Sorry, what's happening to this? Okay, let me draw it. Okay. Okay, this is a damping ratio triangle. Let us say this is phi. Okay. Then we have just seen sine phi was equal to what? Sine phi was equal to, I think, somewhere I have written under root. Yeah, under root of 1 minus xi square. So sine is basically what? This is sine cos tan. Some people have curly black hair to preserve beauty. or Pandit Badri Prasad Hare Hare Bol, like this, whatever you want to remember. So sine is perpendicular by base, but sine is here under root of 1 minus, so perpendicular is 1 by under root of 1 minus xi square. This should be 1 perpendicular by base, sorry, perpendicular by hypotenuse, sorry, this is 1. When this is 1, then this is cos is what? Base by hypotenuse, that should be xi. So we are very clear. This triangle is called damping ratio triangle. You have to remember it. Sometimes it's asked. So let's move further. So when we are talking about C of 0, I can further write it at t equal to 0. C of 0 will be 1 minus, so 1 divided by under root of 1 minus xi square into what? Into sine of phi. Sine of phi is nothing but under root of 1 minus xi square. We know that value. So at C of 0, 1 minus 1 will be 0. So that is at the origin. Your graph will start from the 0 and it will settle down at what? 1 value. That's the steady state value will be 1. Okay. So C of 0 will be 1. So if we have to take the case of underdamped case, okay, that is fine. That is a one case. Now have a look. This, I will box this relationship. Okay, this is a very important relationship for us. This relation, sorry, this relationship is very important. You have to remember it. What is phi? And second, I will use tan phi also as. So let me define the tan also here. Sine we have defined. Here we can obtain tan as tan phi will be perpendicular by base, that is 1 minus under root of xi square divided by xi. So phi value you can also obtain tan inverse under root of 1 minus xi square divided by xi. So you have all the three values. So if you have to include the value of phi here, you can include tan inverse of, everything has to be in terms of xi, then it is tan inverse of under root of 1 minus xi square divided by xi. This is the value of phi. Now case is second case, we will be talking about the underdamped case. Okay, this was, I think this was sorry, underdamped. So we'll talk about the undamped case. Let me talk about the second, undamped. Undamped, what's happening? Undamped, we know that xi is equivalent to 0. So what we are going to get in terms of C of t? So C of t will be 1 minus, I will write it again, xi omega n t. You have to remember this expression now. You have to memorize this. Sine of omega dt plus phi. Phi is under root of tan inverse of under root of 1 minus xi square divided by xi. Okay. So xi will be, in this case, what is happening? Xi will be 0. So xi is 0. This, anything raised by 0 is 1. This is 0. This will be 1. So at C of t, if I am substituting xi is equal to 0, 1 minus, this will become 1. This will become under root of 1 is 1. So this will become sine of omega dt plus phi. Omega dt plus phi. Okay. Sine of omega dt plus phi. So here we can further write this as tan phi is under root of this. Tan phi will be 1 by 0 infinity. Okay, let me substitute the values. I can write it like this: sine, I will write it omega n under root of 1 minus xi square into t plus phi, because that under root omega d value I have told you, we can write it like omega n under root of 1 minus xi square. You can see we have substituted it here. Somewhere we substituted this value for this, yeah, here. For the sake of simplification, that's why I'm repeating here. So, but xi was 0 here, so I can still write it. In this case, xi was 0, omega n, this will be 0 into t plus phi. Now, phi is what for me? Phi I have just now got 1 minus sine omega n t plus tan inverse of under root of 1 minus xi square divided by xi. But xi is 0, so this will be sine omega n t plus tan inverse of, that will be tan inverse of 1 divided by 0. So that will be 1 by 0 will be tan inverse of infinity. Infinity here, because xi is 0 in case of undamped case. So when tan inverse, this will be c of t can further be written as 1 minus sine omega n t plus, that will be tan inverse of infinity will be pi by 2. Tan is at pi by 2 infinite. So sine 90 plus theta omega n t will be cos theta. So I can write it c of t is 1 minus sine 90 plus theta is cos theta. Cos omega n t. This is valid for t greater than 0. So this was the case of what? This was the case of undamped case. So we can find the expression, other expressions also. Okay. So this is fine for us. So that's all. This is what we would have done, and this is what we are expected to do. This is very important expression for us. So let's move further. Okay. Actually, I have a morning also class, health hectic class, tired class. Okay. Thus, what we can say, we can conclude. Thus, we can say, just let me, the steady state value of the response obtained by letting t equal to infinity. This can, we can get x. So let me conclude it. Thus, we can conclude that the step response of an underdamped second order system is damped sine wave. Okay, you can see here. This was for undamped, underdamped here. This is damped. Why damped? Because there is an exponential decay function. This is damped sine wave. This is damped sine wave with initial value equal to 0. That means initially it was 0. And at steady state, the value is equal to infinity, that we have shown in case of underdamped. You can see here, initial value is 0. This was 0 initial value somewhere. Yeah, initial value is 0 here. I can box it also. Initial value is this one, 0. And steady state value at t equal to infinity is 1. Okay, two values we have got. Okay, let me illustrate this step response now. Okay, let me draw it now. Step response of a second order system. दोनों का, for both I will draw. Here, let me draw it like this. Sorry. Okay. So first is for underdamped C of t. Okay. And this is your time response. Here also undamped C of t, your time axis. Step response of underdamped system. This is first. Step response of underdamped system. So this is step response of undamped system. Okay. So how it will be for the initially at this value? Initially it is 0. So let me draw a steady state value somewhere here. Let's say this is steady state value. And this steady state value we know C of infinity is equal to 1 and C of 0 is equal to 0. That we know already. So how it will be, we'll be getting it. We use this curve. So we'll be getting it like this, and then it will oscillate. Oscillations will be there, and those oscillations will die down after when the system will try to reach the unity, when the steady state. So these oscillations will die down. Now in this case, what is happening at c equal to, sorry, undamped case? Undamped case is very simple, so you can see the response. Undamped case, what I have done, c is equivalent to t. Okay, I think we have got the value. Okay, undamped case. Just a second, I want to see we have got the value or not. No, I think we have not got the value for undamped case. Okay, let me get the value for this one so that our graph is more clear. Here I will try to get what was the equation. So at this one, this was the response at t equal to 0. C of 0 was equal to 1 minus, I think, cos of 0. Cos 0 is 1. So that is 1 minus 1 will be 0. So at C of 0, it is again 0. At two points are important for us: initial and steady state. Steady state is infinity. So it will be C of infinity will be 1 minus cos of infinity. Yeah, 1 minus cos of infinity. What's the cos infinity value? Does we have some value or not? Okay. No, just a second. See of what we are going to get the response out of this is undamped case. We are going to get the response. C of 0 is 0. C of infinity. I think this we are going to get the sinusoidal oscillations. Here this is omega. Yeah. This infinity, you check the value. This will be again a sinusoidal curve. What are the value of the infinity will be there? I'm not exactly getting what should be the value here. But if you check this, then if you draw a graph for this one, then it will be, why we are getting, just a second, we should get some value. Actually, I have not calculated it. Just a second. Just give me a 1 minute. So it should be xi. Do we have some value for c of infinity? Should be 1, I think. Uh, 1 plus 1. It will be somewhere 2. It should be 2. Roll number 9. Can you check it?
सर पीरियोडिक सिग्नल्स का कहाँ हम इन्फिनिटी पे निकाल पाते हैं
We'll
लिमिट?
not find it then, but it will be. Let's not
सर
find it for this one.
इस पे लेंगे ना
But it
हम
will be a
ये?
sinusoidal.
यस सर।
Okay, it will behave like a sine. We will not.
सर ये
We will
टू
not find the value.
पाई बाय ओमेगा उन पे निकालेंगे ना
Yeah.
वैल्यूज, वो निकलेगा वो
That
टू।
let us say just 2. ये
यस
multiple. These are multiples of omega. These are multiples of omega. Is it clear or not?
यस सर।
But we'll be getting some value, and that value, let's say it's a 2 value we are getting. अगर हम पहला ही ले लेते हैं, we can go for the next peaks also. But if we are writing some values, then let's get the value. मैंने निकाला नहीं है ये 2. Let's say this is a 2. Books normally normalize 2 ले लेती हैं, या this periodic value he can take for this one. So what's happening here? Initially it is starting, then there will be, you can see there is if you leave this one, this is still 1 minus cos is still a cos, a curve is, this is a cos curve. So we can just put it like this. There is no damping at all in this case, so nothing will happen in this case. प्लीज मेक श्योर ये इतना अच्छा नहीं बन रहा है यहाँ से, क्योंकि दिस शुड बी okay, but this is a sinusoidal case. Okay, this is the response of the 100 amp. So I think this is very clear. There is nothing. Derivation में कोई problem है? हाँ जी, roll number 6.
नो सर क्लियर है।
Okay, ये clear है, ये इतना different mathematics it's a pure sort of mathematics. Okay, now let's talk about the overdamped now. Second, overdamped case. Okay. Now, overdamped case, when xi is greater than 1, the system is said to be overdamped. This you know already. Is said to be overdamped. Okay. The closed loop poles also you know. What are the closed loop poles? Are real and unequal. Are real and equal when xi is greater than 1. That we have already seen. Then the closed loop poles of the overdamped system is found by equating denominator polynomial. So equating denominator polynomial of closed loop transfer function to 0. Closed loop CLTF is closed loop transfer function to 0. That means we mean that s square plus 2 xi omega ns plus omega n square should be equal to 0. So that will give us the closed loop poles. Call them. So poles will be s is minus b, 2 xi omega, and coefficient of s plus minus under root of b square That will be 4 xi square omega n square minus twice ab. Twice a is 1, b is, that will be 4 xi omega n. Okay, twice, sorry, b square minus 4ac. 4 is this, 4 a n c. This is c is n square. Okay, omega n square. So that will be divided by 2a. Coefficient is 1 for a. So if we get the root number 1 will be minus xi omega n, because it will be divided by 2, minus omega n under root of 1 minus xi square. You can see clearly 2 will be divided, xi omega will be here, minus plus part. So what you can take common? You can take 4 xi omega and you can take common. Out of that 2, out of the 2 will go. So that will be xi, sorry, you can take xi square, no, xi, you can take 4 omega n. Out of 4 omega n will be 2 omega n outside. So that will be xi square minus xi. That will be xi into xi minus 1. So xi square minus 1 you can write down inside. There's no problem. Yeah. Why is this xi we are getting? Where from this are we getting? Just a second. 4ac is there. So a is 1, c is omega n square. 4ac. 4ac is b square minus 4ac. Okay. So 4 n square we can get 2 common. So that will be 2 omega n. So 2 will get cancelled. Omega n will be left here. Omega n inside will be, so that will be xi square minus 1. So why I'm writing xi square? Yes. Okay. So that will be 1. And second, we can get in the similar ways as minus psi omega n minus will be plus now. Second root omega n, same xi square minus 1. Okay, these are the two roots. Next, the closed loop transfer function of the system. Therefore, the closed loop transfer function of the system in the factorized form in the factorized form is given by, let us see, so C of S by R of S will be equal to omega n square S square plus 2 xi omega ns plus omega n square. That will be omega n square S plus S1 S plus S2. Fine. So this is S plus S1. I have given what is the S1 and S2 above. So let's see what is C of S now. Now this is R, 1 by R of S is 1 by S. So that will be 1 into omega n square S S plus S1 S plus S2. No need to write this one. We know 1 by S is a step response. Okay. So if we use a partial fraction, we are not interested in calculating the values. Using partial fraction expansion, using this partial fraction expansion, what we are getting, we can write C of S as K1 by S plus K2 S plus S1 then K3 or S plus, sorry, this is S2. Okay, so let's call it equation 1. So these constants, you know how to find them, we are not getting. So constant values K1, let us say we will get equal to 1. I'm not calculating, you need to do it yourself. K2 will be, it will take time, 1 divided by 2 under root of xi square minus 1 into xi plus under root of xi square minus 1. So this is the K2 value. And K3 value will be 1 by 2, that's the minus root here, 2 under root of xi square minus 1 into xi plus under root of xi square minus 1. You are requested to find these roots yourself, please. Okay? Then taking Laplace inverse, we will get C of t equal to K1, 1 by S is 1 in inverse K2 e raised power minus S1 of t plus K3 e raised power minus S2 of t. Let us call it equation number 2. If you substitute the values of K1, K2, K3, what you are going to get? Substituting K1, K2 and K3, the response what you are going to get is 1 plus, that's what we are interested in, 2 under root of xi square minus 1 e raised power S1t by S1 line minus S2t by S2. That's for t greater than 0. Now overdamped response, what will be? What is this sorry. Yeah. S1 is equal to what? Yeah, S1 is this. So you can substitute this value here. If we see, initially, this is e raised power 0, 1. E raised power 0 is 1. So this somewhere initially is going to come out 0. This value, if you substitute complete, it would be 0 initially. Then finally, at C of infinity, it will be equal to 1 because e raised power infinity is 0. E raised power minus infinity is again 0. 0, 0 multiplied by this will be 1. So that's what we are responsible. We'll draw the response of this one. Like this, we can draw the response. I hope you can substitute the values at initially it will be 0, there will be no question at all, and then finally it will settle down at 1. So this is your response for overdamped, and somewhere we'll be putting the steady state value as C of infinity is equal to 1, which is clearly 1. E raised power minus infinity is 0. E raised power minus infinity is 0 minus 0 is 0. Multiplied by this thing will be 0, and it will be left with 1. So critically damped, what will happen? It will increase like this, and it will take some time to reach to the response like this. Okay, that is step response of an overdamped system. Critically damped, it will take some time and reach to the steady state value. Sorry, not critically damped, over damped we are talking about. Over damped, it will take some time. So similarly, we have a critically damped. I think अभी किन का क्लास है आपका? It's taking time because ये derivation बहुत बड़ी है. Yes, तंजीब
Yes, sir. Yes, sir.
किन का क्लास है?
अरे last class.
Okay. So we are left with critically damped case. अगर हम थोड़ा सा 5 मिनट लगते हैं, then we will have time domain specifications to do in the next class. ठीक है, तो उसमें भी 2-3 डेरिवेशन है, देन बाद में टाइम नहीं. वी विल डू दिस, आई थिंक जल्दी जल्दी इसको कर लेते हैं. नेक्स्ट इज अ क्रिटिकली डैम्प्ड केस. इसको खत्म कर लेते हैं अब, अदरवाइज विल बी अनदर प्रॉब्लम फॉर अस नेक्स्ट टाइम. critically damped case. Okay, in this case, what we are doing, what is the critically damped case? Xi is equal to 1 if xi is equal to 1, the system is said to be critically damped. System is said to be critically damped, and you know that when the system is critically damped, then the closed loop poles are real and equal. We have already seen this. Okay, and then the closed loop transfer function of critically damped system is given by C of S by R of S will be equal to omega n square s square plus 2 xi omega ns plus omega n square. Now we know that xi is equal to 1. So this will further become omega n square s square plus 2 xi is 1 omega ns plus omega n square. So we can further write it omega n square divided by s plus omega n whole square. Okay, so using the step input, r of s is 1 by s omega n square divided by. Okay, so now this is equation. We can use the partial fraction again, and I will be taking the inverse. You can do that yourself, taking Laplace inverse. So that inverse will be, I will be writing the response 1 minus e raised to power minus omega n t 1 plus omega n t. That will be the response. Okay, in the time domain. So if we draw the graph of this one, okay, this is C of t. This is infinity will be again 1. Can very clearly see. C of infinity is 1. This is 0. This is time. Okay, so this is critically damped. This will be faster as compared to the overdamped. Okay, it will be, sorry, it will be like this. There will be no oscillations at all. So this will be, response will be like this. So this is step response of critically damped system. So 0 can be also taken, 0. It is about 0 is 1, 1 plus 1 minus 1 is 0. So this is, graphs are very clear. You have to just use the relationships. Okay, that's all. So next we will have a time domain response specifications, rise time and other things. Let's stop this. Tanzib of log